Hello and welcome. In this lesson, we'll explore some applications of exponential functions. First, we'll take a look at this equation. Whenever we analyze application questions that can be modeled by exponential functions, this will be the equation that will help us solve the problem. So let's take a closer look at it. A equals I multiplied by B to the power of T divided by P, where A stands for accumulated amount or the final amount. I stands for initial or principal amount. P represents the time period, whereas T represents the total time. And we'll talk about the difference between P and T, since they both represent time, in the examples that we'll discuss together. B, on the other hand, is what we call a factor. It is represented by a number that is positive and different than 1. Imagine if B is 0, then this will make it a linear function, and same with 1. Now, the values of B bigger than 1 represent exponential growth. The values of B less than 1 and always bigger than 0 represent exponential decay. Now, the growth rate indicates the amount in percentage of population is increasing because it's growth. Now, B is the growth factor, or we can think of B as a multiplier that indicates the amount in percentage after one growth period. To determine the growth factor, which is the value of B and is the number we need to input in the equation we're using to solve the problem, we add 1 plus R when R is expressed in decimal form. For example, if a population is increased by 10%, then we say that R equals 10% or 0.1. The value of B will be 100% of the population, what it was before, plus 10% of it, which makes it 110% or 1.1. Or we can look at it as 1 plus 0.1. So this is the reason why we add 1 plus R when R is in decimal form. The decay rate indicates the amount in percentage of population is decaying or decreasing. The decay factor is again a multiplier represented by the letter B in the formula that indicates the amount in percentage after one decay period. To determine the decay factor, we subtract R from 1. For example, if a population is decreased by 10%, it means that the value of R is 10%. And the population will go from 100%, take away 10%, which tells us that in the next cycle we have only 90% of the population left, which can be represented as or described as 1 minus 0.1 if we use the decimal form of the rate, and that would be equal to 0.9. We use the decimal form of the value of B in this case. Half-life is the time it takes for a population to become half of its initial. To decrease by 50%. So you can interpret it in multiple ways: to decrease by 50%, to become half of the initial. The value of B in half-life model is always 1/2 or 0.5. Doubling life, on the other hand, is the time it takes for a population to double. To double in size, right? And as you might have guessed already, the value of B when a population is doubled will be 2. Let's take a look at a couple examples together. An island colony of seabirds increases by 75% every 2 years. Today, it has 1,200 birds. How big will the colony be in 10 years? How big was it 6 months ago? So let's read the information and try to interpret all the numbers. Whenever I see the word by in the problem, then that would be the rate. Because the population is increased by a certain amount, so that would be the growth rate. This will help me find the value of B because that's what I need to use in the formula. So the value of B, and I'll find it in multiple ways, is 100% plus 75%. Or we can look at it as 1 plus 0.75. Or we can say B equals 1.75. Next, we have every 2 years. So always pay attention to the numbers given in the problem. Every 2 years means that every 2 years the population will increase by this amount. And whenever you see the word every in a problem, then we will think of the number or the time length after the word every as the period. Because that's the period of time for a population to experience one growth by the indicated amount. So the period will be 2 years. And period is indicated by letter P. So next, today the population is 1,200 birds. That means that the initial population is 1,200. We need to know how big will the colony be in 10 years. So how big will it be means that we are trying to find the future population, the final or the accumulated amount. In 10 years means that we're trying to find the population 10 years from now. So that would be the total time. So now that we have all the information organized here, what we're going to do is use the formula. A equals I, B to the power of T over P. A equals 1,200, B is 1.75, total time is 10 years, and period is 2. It is very important that the time period and the total time are measured by the same units. Use the calculator to find the answer. Be very careful with brackets. When you bring to the power of 10 over 2, you need to bring this in brackets, or you can simply simplify 10 over 2 by 5, but sometimes you may end up with some decimal numbers. I prefer to keep this number in exact form. So the population 10 years from now will be 19,695. And I will round it to the nearest whole, and I will round it down because it's about a colony of living things. We'll take a look at the next question. We're still using the same formula. But this time we're asked to find how big was the colony 6 months ago. So the total time this time is 6 months. And 6 months translates to 0.5 years because the period is given in years. Now, another word that you probably notice here is the word ago. So we're going back in time. So it would make more sense then to let time be negative. So now we'll say the population A equals I, B to the power of T over P. We use the exact same formula. And we want to find the population of 1200 from now that normally increases at 75% rate, or B, a 1.75 factor. The time t is negative 0.5 divided by 2. Use the calculator again, and we'll have 1200 multiplied by 1.75 to the power of negative 0.5 divided by 2 is 1043, and we expect to find a smaller number here.